All right, let's look at another example where we use the first and second order conditions in order to find a minimum this time. So we want to solve for the x star that will give us the lowest possible risk. So once again, what we have is a case where we want the slope to equal 0. And in this case, the second derivative evaluated at x star should be positive. So we start with derivative going negative to flat to positive. So as we go from left to right, as the x goes from left to right, we see that the slope is increasing over x. So that's a positive second derivative. All right, so we're going to look at a case where we have two risky assets. All right, and we're going to have the risky assets, and here are our exposures. So our proportion of wealth in asset 1 and asset 2. So we're going to say that we're going to invest 100% of our wealth in this portfolio, and what we can do then is back out what x2 would be, which would be 1 minus x1. All right, so we have a situation where the variance is going to be our exposure to asset 1 times the variance of 1, our exposure to asset 2 squared times the variance of asset 2 times the covariance of our exposure to asset 1, our exposure to asset 2 times the covariance between the two variables. So this is the expression for the covariance of a portfolio of two assets. So what we've done, though, is we've said that we've expressed variance in terms of only one variable, x1. And so given this condition over here, and once we solve for x1, we plug into this equation and we get our exposure or portfolio weight to x2. All right, so let's see. The derivative, this with respect to x1 is going to be, I want to get out of the eraser, it'll be 2x1 times the variance of x1, and this I think we can write as 2x1 minus 2x1 squared. So we can write this as, say, 2 minus 4x1 times the covariance of 1 and 2. And then over here, how can we write this? 1 minus 2x1 plus x1 squared. All right, so we take the derivative with respect to the x1s, and so what we have is a negative 2 plus 2x1 times the variance. All right, so here we found our first order condition, and now we're going to take the derivative and set it equal to 0. All right, so, wow, I don't know where I got this. Okay. All right, so I think I do. All right, so one thing we can do is we can factor out our 2's or divide both sides by 2. So we get, x1 times the variance of asset 1 plus the covariance minus 2 times x1 times the covariance plus or minus 2 times the variance of asset 2. We factored out the 2. That should be a 1 plus x1 times the variance of asset 2. All right, so this is still set equal to 0. So let's just factor out the x's. So we got x, and we have a variance of x minus 2 times covariance plus the variance over here. And then we have negative the variance of asset 2 plus the covariance matrix. All right, so All right, we set that equal to 0, bring all this stuff over there, divide both sides by what's in the interior, and what we have is x1, the optimal x1. It's going to be the variance of asset 2 minus the covariance of 1 and 2 times this expression that was inside the parentheses. All right, and so it turns out that if the correlation between asset 1 and 2 is less than 1, this will always be positive, and that's going to be positive. So, this will be a positive weight. All right, so that's the first order condition. So we found our minimum. And so if we look at this relationship up here, does the second derivative equal value that's greater than 1, or greater than 0, I should say. So we take the expression up here with respect to x1. So what is that? It'll be 2 times the variance of the first asset minus 4 times the covariance of the two assets plus 2 times the variance of asset 2. All right, so this is basically 2 times, well, it turns out it's going to be the variance of the return on asset 1 minus the return on asset 2. All right, so if the correlations are different than not exactly equal to 1, this is going to be a positive number. All right, so the second order condition is going to be positive whenever correlation is not equal to 1. Okay, so that's finding a minimum value using first and second order conditions. Okay, so we'll stop there.